In this section, we're going to talk about logarithmic functions. These tie very, very closely to exponential functions. In fact, logarithmic functions are inverse to exponential functions. So inverse means it's just reversing the operation. So let's say we have an exponential function, y equals b to the x. How this works is that we input an exponent, and then with that base of b and that exponent of x, when we calculate it, we get this output of y. So we end up with this kind of setup where I'm going to call y the value. So we end up with a value, and that equals, and we have some base with some exponent. So the purpose of this function is to solve for that value y, given some base and then plugging in some exponent. So what we want is to reverse our input and output in terms of the exponential function where the input is the exponent and the output is the value. How do we switch it so that we input some value and we can end up solving for an exponent? So we want a function where the output of the function would be an exponent, and that's what logarithms do. So we have this format down here of x equals a logarithm with base b of y. So with the logarithm, there's some different notation here. So there's this, we call it kind of a subscript here for log. That describes the base of the logarithm, which matches up with the base of our exponent. And then we're taking this logarithm of y. You could even imagine some parentheses here with y in there, where y is the value from our exponential piece. And then the idea is that we're solving for our exponent. So how I could rewrite this in words is that we're solving for an exponent, and that is going to equal some logarithm. So for our notation, we use log, and then we're going to have some base, and then we're taking that logarithm of some value. So the idea is that when we look at a logarithm, we can see a base, we can see a value, and we want to fill in the blank for what exponent makes that base and value work together. So when I read logarithms, I often say to myself, like, what exponent is needed on the base b to get the value y? I just finish my writing here. Okay, this is what logarithms are asking. What exponent is needed? And we're raising b to that exponent to get out that value y. So these two numbers are working together with the logarithm, and we want to fill in the blank on the left-hand side of the equation there. So let's look at some examples here. So on this left-hand side, I have the exponential form, and on the right-hand side, the logarithmic form. So we know the relationship 2 raised to the third power is equal to 8. How I would rewrite that in logarithmic form is we would have a log with the base of 2, just like how 2 is the base of that exponent of 3. And then the value is that value 8, which was the end product of having that base with an exponent. And then that equals that exponent of 3. So we can follow those pieces where we have that base of 2 that ends up being the base of the logarithm. That exponent of 3 ends up being on one side of the equation, and that value of 8 that came from that calculation of 2 cubed is what's inside our function of that logarithm. Similarly, 5 squared equals 25, so 5 would be the base. 2 would be the exponent since it's 5 squared, and then we're getting a value of 25. Writing that in logarithmic form, so we would have log, and we're using a base 5 logarithm of that value of 25 is equal to that exponent of 2. So the idea is if I just wanted to simplify the logarithm base 5 of 25, I know the answer's right up above there, but let's say we didn't have it, but just to refer to something we've already solved, seeing that base of 5 with that value of 5, what I'm asking myself is basically 5 to what exponent is going to equal 25. So we're trying to fill in the blank for an exponent there, and it would be the fact that 5 squared would give us 25. So we can have these different bases, but there are two bases that commonly come up. If you see logarithm of x and there's no base described there, we assume that that's a base of 10. So you won't really see log base 10 of x. Since base 10 kind of commonly comes up, we just call that our common logarithm. So instead of writing log base 10, you'll just see log of x. Or more precisely, if you see log of x and there's no base described, you're using a base of 10. Another common base that comes up is a base of e. So we use base e. This is going to come up in a lot of word problems especially. And with that, we use a special notation for natural log of x, which is ln of x. So having like log base e of x, we just write that as ln of x for natural log. Okay, so there's some basics of logarithms. So let's try switching between our exponential and logarithmic forms for these various examples down here. So this first example, we have 3 with an exponent of t equals 5. So let's see, 3 is our base, t is our exponent, and then 5 is the value that we get out. And what I want to do is change this to logarithmic form. So this is going to be a logarithm with base 3. So logarithm base 3. And then our value inside of the logarithm. So we're taking log base 3 of 5. And that's going to equal that exponent of t. So if we were solving for t, this is what we would use here. So we could solve for that exponent to figure out what value fits there. We'll talk more in the later video about how to actually evaluate that number in a calculator. Maybe we'll even come back to this example here. But for now, I would just leave it like that because there isn't a nice whole number that fills in the blank there. But if we could solve for t, we'd want to. Okay, 10 raised to the power of m equals 7. So we have base of 10, exponent of m, and a value of 7. So changing this, we're going to have log base 10. So with that, I don't even need to write anything for the base. I'm just going to write log. And then our value is 7. And then that's going to equal that exponent of m. And actually, this one we could evaluate in the calculator. Let's go ahead and do that while we're here. So with our calculator, we're going to run into, and let's see, if we're at our Desmo Scientific Calculator, there's a few ways to go about it. If you go to the functions menu, you'll see there's our natural log, ln, and there's log for log. I usually don't navigate to the functions menu. You can just type it in with the keyboard. So like log of, and I believe it was 7. And what we can get from our calculator is a decimal. So in this case, it's a 0.845. So the idea being, if we had 10 raised to a power of 0.845, yeah, we get something. It's a little off because I rounded there. In fact, maybe I'll write more decimals. 0.84509.804. There we go. Once I had enough decimals in there, that brought us to our value of 7. So 10 raised to that exponent gives us 7. So that kind of checks it. So what we could do is evaluate log base 10. We can evaluate natural logs in the calculator, but where we get stuck is when we start changing the base to different values besides 10 and e, and that's where we'll use something called the change of base formula, which we'll look at in a future video. But since I was log base 10, we could put that into the calculator So in fact, let me write one more step there. Even though they didn't ask us to solve, we got that m was about 0.85. And there were more value. 8451. Let's do that. 8451. All right. Okay, for this one, we're given the logarithmic form. So we have log base 3 of 5 equals x. So the 3 is our base. And something that people use to remember that that's the base value is that it's like appearance-wise, it's in the basement. It's kind of below the logarithm as this subscript. So we have 3 in the basement, value of 5, and then whenever we solve for a logarithm, whatever's on the other side of the equation is an exponent. So switching to exponential form here, we have base of 3, exponent of x, and then equals, and that value of 5. Okay, and then we would just leave it like that. With this, we have 1/4 raised to the power of x equals 6. So that 1/4 would all be the base. We have an exponent of x and then a value of 6. So switching to logarithmic form, we're going to have a log base of 1/4 or 0.25 of 6 equals that exponent of x. All right. Hopefully you're getting the hang of these, and if you even want to pause here and try these last ones for yourself to make sure you got it, that would be good to do, but I'll keep going through these solutions. All right, log of x equals 1/2. So again, it's not written here, but really there's a base of 10, and then we're taking the logarithm of x, so x would be our value, and then logarithm equals, and then whatever's on the other side is an exponent. So exponent of 1/2. So what we're doing here is we have base of 10 raised to a power of 1/2 equals x. Actually, that's just the square root of 10. We could even plug that into a calculator if we wanted to actually solve for x. But I'll just leave it like that. All right, e to the 2t equals 5. So we have base of e, exponent of 2t, and then equals a value of 5. So we're going to switch this to a logarithm. So this would be a logarithm with base e, which is our natural log. So I'm going to write this as ln. And then we're taking the natural log of that value of 5, and then equals 2t, that exponent. And actually, we could solve for t here. We could divide both sides by 2. So if I did that, t would be equal to the natural log of 5 divided by 2. And that's something I could plug into the calculator as well. So let's take a look at that. So we're going to have a fraction with natural log of 5 in the numerator. And I just typed in ln 5, so it knows to evaluate that as a natural log over 2. So that's a 0.8047. And then the idea would be that we could take that value and plug it in. So if I go back and go e to the power of 2 times that 0.8047, that should equal about 5. All right, logarithm base 2 of this value is an expression, y plus 1, and then that's equaling -3, which would be our exponent. So we have base 2 to the -3 equals that expression of y plus 1. And then we could actually simplify this. So 2 to the -3 would be 1 over 2 cubed. So that negative exponent just moves it to a denominator, y plus 1. So that would be 1/8 equals y plus 1. So subtract 1 from both sides. So 1/8 minus 8 over 8, so -7/8. Yeah, so we could solve that one. So notice some of these I can solve. It's really the ones with the logarithms with a different base where we don't quite have that information yet. Okay, natural log of x equals 5. So this has a base of e, the values inside the logarithm, which is x, and then logarithm equals, and that's going to be an exponent. So we have base of e to the power of 5 equals x. And this is another one, we could plug this into the calculator. We just need e to the 5th. So if I go and just type in e to the power of 5, 148.4132. 148.4132. Think I remember that correctly? Okay, so I know I use lots of colors here so you could follow those, but just base of an exponent lines up with base of the logarithm. The exponent, this is going to sound weird, but the exponent in the exponential form is going to line up with being one side of the equation. So whenever you have logarithm equals something, that something is an exponent. And then we have this value that's the output of an exponential form. It turns into the input of our logarithm. So if it's on an exponential form, if it's on one side of the equation as just this value, this number that comes out, then when we switch to logarithm form, it's going to be inside the logarithm. The logarithm's a function, and that value will be the input.